Hey guys, how was your long break? I guess it wasn't long enough. We did miss out like 2 days. Who went out of the country? Raise your hand. Oh, where'd you go? She went to Mexico. You went to where? Italy. Yeah. Did they bring us back anything else? Okay. I did get 2 pictures from you guys. Thanks. Keeping me up to date on how you were doing over break. I tried to send you a picture of my husband, but the wind was crazy. Anybody else need peppermint? It helps activate your brain.
Good morning, teachers and students. Please pardon this interruption. Freshmen, we want to make sure you know that the registration form will be live starting at the end of today. If you try to log in today, you will not be able to do the registration form until the end of the day. At this time, freshmen will last name E through K. Please come to the auditorium for your large group advisement. Freshmen, last name E through K. Thank you.
All right, guys, so let's kind of start with wrapping up a couple things from over break, before break. That's right, or what was it, Tuesday or Wednesday, whatever day we had, the last day right there. You guys worked on a couple of assignments that were, you were finishing up in class, and then I said you worked on Tuesday and Wednesday, and then you guys should finish what you could. On here, I will review whatever I need to review with you, but in preparation for our midterm, I'm trying to make sure that we get to this like final topic that we're supposed to be working through before next week. So as a reminder though, you should know how to find the pH of basically anything at this point. There's one thing we haven't learned is buffers. That's what we're going to learn a bit more about tonight and then tomorrow. But does anyone have questions about what I'm looking for here? Some of it might be in your packet, and I understand you might need to hold on to that because you might need some of the information out of your packet. But I'm going to be looking at that for completion and a little bit of accuracy, so just make sure I get those. You can staple them or paper clip them, but just don't put them in the box just yet. Just keep it on your desk for now. So the NSMI packet questions, those have the answers at the bottom, so you should have been able to self-check many of those. So salt hydrolysis questions, most of those we got done in class, and the answers are at the bottom. The textbook questions are just for continual practice. Those are all, almost all odd, the odd answers from the back of the textbook. And then I just said a couple of those pHs of mixtures. There were a couple of you guys who asked me questions on the equation writing right before break, so I think that you're okay with writing your double replacement reactions or whatnot. So we're going to kind of jump back into chemistry. I know you're like, oh gosh, we have a whole other semester, but we definitely have done the hardest of the hardest, okay? The last bit we're doing is buffers. After that, in January, I planned out everything through the end of January for us, so we'll have our buffer test January the 30th. Which is our acid base and then applications of acid and bases and buffers. We'll have that test on January 30th, but you'll have some of that on your midterm a little bit because of the fact that, if we talk about it in practice and it's fresh, then I'd like to see if we can touch base on that. When is your midterm? Next Tuesday, right? Not next Tuesday, no. The following, yeah, the 17th, okay. And it's a full-length AP exam, and because this is, this whole semester so far, we've covered things that are somewhat prior knowledge, like reactions, solutions, acids and bases, gases, thermo. But then there's that additional stuff that was like advanced thermo, advanced gases, advanced acid and base equilibria. So that's what this test is going to be. I think I cross my fingers harder than the AP exam, because we haven't covered the easy stuff yet. I would say the easy stuff for spring, when you're like, I'm out of breath now, I'm low, I can't do anything else. So coming up in January, end of January, beginning of February, we have electrochemistry, which is just applications of oxidation reduction, just transferring electrons, making batteries. It's really cool. You can make pure gold. I mean, not gold, sorry, silver. And then pure copper, we get to make a couple of interesting metals. And then after that, we have like atomic structure, protons, electrons, neutrons, electron configurations. You guys remember this? The light equations, the Bohr model. Remember the Vesper theory where you have like tetrahedral, bend, trigonal planar shapes and stuff like that. And then intramolecular forces like on steroids, okay, so like hydrogen bonding, London dispersion forces, dipole-dipole forces, remember a little bit of that? Between molecules, intramolecular forces. Some people are like, yeah, no, okay. And then the last bit is colligative properties with freezing point depression, boiling point elevation, delta T is equal to KIM. Remember a little bit of that? Okay, some people, it depends on what class you're in, how in-depth you got, but we're on the tail end, okay? So we're doing great. And actually, I've planned, and I looked at our kind of year plan. We are one day ahead, according to what I have planned through January. So we'll try to stay there. That way you get more time for review at the end of the year with me. So let's kind of just jump into some review. You can see that today we're just going to talk about some of the mixtures that we need to kind of recap how to find the pH of. I have some diprotic examples because you guys were like, we don't want to do any examples last week or 2 weeks ago. We just kind of talked about diprotic acids. And our lab today is going to be reinforcing our pH and also knowing how to use a pH probe because we're going to use pH probes more extensively here in a couple of days. So you guys have this in your packet. Okay, take maybe 10 minutes, not quite 10 minutes, and you can talk in your groups about this, or you can write them down. So this is in your packet. It's the lower left-hand side on the very first part of the packet. Lower left-hand side. And I am going to talk about genetics tests as soon as I can. I'll let you guys get started without me first. You guys know where this is? No, this is your first one. Chapter 14, recap. So you can talk in groups about it, or you can write it down. Yeah, be careful. I got acids and bases all on the spot. It's on my website too, so I can look at that shortly. All right, you're going to talk to me in groups here, okay? So we're going to call these group 1, group 2, group 3, group 4, group 5, and then AJ group 6, okay? So I'm just going to go with the flow here. So tell me the difference between Arrhenius, Bronsted, and Lewis acid-base group 6. As quickly as you can, though, okay? So, yeah, group 6 is tell me number 1. Okay. Okay. I'm just going to put H plus as a proton. Okay. What does Arrhenius do? I'll come back to that group. Group 5.
They form the H plus and O minus.
I'm going to say hydronium or hydroxide in what? Aqueous solution, right? Remember, Arrhenius aqueous means how does it behave in water? In water, acids make hydronium, and water bases make hydroxide. And then Lewis is discussing the difference, kind of a different perspective, but it's referring to what? Thingy's group?
Electrons.
Electron pair, right? So electron pairs being accepted or donated, and it forms a bond. It's a coordination or a coordinate covalent bond, but it does form a bond. That's different though. We'll kind of jump on that soon. Hydronium ion, I got that one, H3O plus. It's just basically a water molecule with a proton added to it. Levi's group, what's a conjugate acid base pair? And you can give an example that helps with that. Okay, so NH3 compared to NH4 plus. What's the difference between this? So the conjugate acid base pair is the difference between the two molecules is just one H plus. So don't get crazy and try to make a totally new acid or a totally new base. It's the difference of one H plus. So the conjugate acid base pair is correlated with what definition? Arrhenius, Bronsted, or Lewis? Bronsted, because it's talking about the proton, talking about the difference of a donation or an acceptance of an H plus. What is Ka, Avery's group? So the equilibrium constant for an acid is a decent way of saying it, but I was hoping maybe a little bit more descriptive. And only because the vocabulary sometimes throws us off because we don't say the different versions of how things are called. So this is called the acid dissociation constant. But it does represent how an acid undergoes a reaction with water at equilibrium to make products of an H plus and whatever the ion is. But it shows us the extent of the forward reaction, right? So our K is negative. No. Never. Okay, so K is either greater than 1 or less than 1. If it's way greater than 1, what does that tell us? It tells us it's a strong acid, but it tells us why is it considered a strong acid if the K is greater than 1? It dissociates basically 100%, right? So a lot of products, no reactants left over. A low K value means it's a weak acid, so less than 1 means a weak acid, not very many products are made. The reactants remain intact, meaning nothing really dissociated, nothing really ionized. That's probably a good one to remember. Difference between strong and weak, we kind of just said that, dissociations, 100% versus not. We call that percent ionization as another way to describe the amount of dissociation. What is a diprotic acid? Allie's group? So sulfuric acid is a diprotic acid, so it's got 2 H pluses or 2 H's in it. Good. Organic acids are generally what, everybody? Generally weak. Can someone give me an organic acid? Acetic acid. Good. So HC2H3O2 is an organic acid because it's got carbon in it. It also has that acetate area, which is fairly low in its electron density. So the bond between the H and then the acetate, this bond between the H and the acetate is what? Say again? Strong, meaning it doesn't dissociate very well. There's not a whole lot of electron density in that acetate, so it's going to be able to hold onto its H plus fairly well. Amphoteric means what? Group up here? Right, like you can rub both hands, you can act as an acid or base, meaning you can accept or donate. Many times water is written as, or is always described as amphoteric. KW, what is the value of KW, everybody? 1.00 times 10 to the negative 14th. Good, that's called the KW constant. We use that when we compare KAs and KBs, right? So KA times KB equals KW, and so that relationship is used a lot of times in salt hydrolysis. When calculating pH from H plus, how do you determine the total number of sig figs? Anybody? Say again? So the sig figs are in the pH after the decimal. But how do you determine how many decimals there should be? What's it based on? Right, in that first initial concentration, right? So if it was like 1.002 molar, you'd have how many sig figs? 4, right? 4 sig figs in the concentration, so you have 4 decimals in the pH. Okay. pH of a strong acid differs than that of a weak acid. the calculations are different, right? So this is us kind of reviewing quickly how do we calculate different pHs of different solutions. How do I find the pH of a strong acid, Arshia? Just the negative log of the acid's concentration, right? Just go with the flow. That's what we did in honors chem. Alvin, how do I do it for a weak acid? You use Ka and you have to set up a ice box, right, to get your products and your reactants. You have to minus x, solve for x, and x equals what ion in your ice box? H plus. And so that's your concentration, and then you plug it into your pH is equal to negative log. A little bit more elaborate, right? So that's one thing we just got to make sure we're practicing. Let's see here, what else do we really need? Oh, how do you calculate percent dissociation? Anybody? Okay, so solve when you solve for x by neglecting, you get x and then you and I'm going to say divided by the initial acid molarity because it's the amount of that acid that associated. So percent ionization is based off the acid given. So that and then times 100 of course for percent. Calculate pH of a strong base. pH is equal to 14 minus POH, right, which is negative log of OH concentration. And then salts that produce acidic, basic, and neutral solutions. So Lucas's group, give me one of the salts and tell me if it's acidic, basic, or neutral. Your whole group can help there. And then Alvin, your group's next, and then Jack group. Just give me a salt. Sodium chloride. Okay, so sodium chloride, is that an acidic, basic, or neutral salt? Tell me how you break it down and to think about where it came from. Because remember, salts are made from acids and bases. Acid-base reactions make salt and water. So what acid came into this to make sodium chloride? Hydrochloric. And what base was also present to make sodium chloride? Okay, so if you know those are the parents to make this baby salt, this is a strong acid. This is a strong base, so it's a neutral salt. Binky's group, or Alvin, somebody back there tell me an acidic or a basic salt. Potassium chloride, because potassium comes from potassium hydroxide, and HF, hydrofluoric acid, makes the F ion here. So this is a strong base, and this is a weak acid, so it makes basic, right? And then Jack's group. Give me a, what did I say, an acidic one. Anybody can add if you guys have one in your head. Aluminum chloride, I'm doing that because this comes from AlOH3 for our weak base, and this comes from HCl, which is our strong acid. Strong acid wins. It's going to be acidic. Okay, so that's how we hypothesize the pH, but then we actually calculate the pH of a salt by choosing the ion that reacted with water to actually do something. And so, for example, what ion in KF would react with water in a strong forward reaction? So this is K plus and F minus, right? When both of these react with water, what happens? Go for it, Courtney.
When you get KOH person.
Okay. Okay, so which of these half reactions or partial reactions makes a strong product that would reverse the reaction through dissociation? The first one, right? This KOH is not going to stay as is. It's going to immediately ionize and basically just reform what it initially had. So to scratch that out, not important. I call it no reaction because we know that literally nothing really happens. This is the reaction of interest. This one makes a weak acid. The weak acid doesn't ionize. It doesn't go back. So we have a reaction happening. So then you take your initial concentration here, minus x plus x plus x. You set up an ice box. But F minus is acting as a what here? Acid or base? Acting as a base because it's accepting, right, taking the H plus back. So if it's acting as a base, I must find the Kb of, after making it act as a base, right? So I have to find the Kb, but F minus doesn't necessarily have a Kb established for it because it's not really a base, it's just acting as a base. But I know that this right here is its counter ion, right? It's a conjugate. This has a Ka established for it on your Ka sheet that you have. So you'll find the Ka of the find the Kb of the Ka for HF, and then that would be what you use for your icebox. Yeah. Yes, because one, it's acting as a base because it's accepting, and then also additionally it's making hydroxide. It's acting basically must correlate that with the appropriate dissociation constant. And how would I find Ka from K or Kb from Ka? Kw, right? So Kw over Ka would give me Kb, and then I plug in, find X, find OH, backtrack to H plus, and then find the pH. So salt hydrolysis is always like the worst because it takes a number of steps to get there. Okay. So that feel pretty good that you kind of bringing some of it back to Zap a little bit. Okay, last thing, I want to make sure that you're cool with talking through how to find the pH. I don't want to find these pHs right now. Tell me how you would set them up, okay? So I'm going to ask you guys to do this in groups first. So you guys decide 1, 2, Jack 3, 4, 5, 6. Talk for 30 seconds, and then you're going to tell me how you find it. Cool. Okay. All right, back with me then. I think we're probably good. I just want to do one double check. So whenever you're whenever you're looking at a problem, you guys will have to find, like I said, pH of literally anything. So first you need to identify what it is. That way you can target, like I can categorize what it is, and then from there you know the method that's used to solve for that pH. So first group, you guys said this is a weak base. Okay, so for weak bases, you have to do what to find their pH? Icebox with K, because that will be given to you as a base. You are always given the Kb with it as well, and then you'd solve for, and that equals, and then you do 14, right? Minus pH. Cool, nice. Binky's group. Hold on, identify this first. This is so this is definitely just simply that aniline, anything with an amine group on the end. Where have you guys heard amine before? So let me backtrack for a second. Amine. Think biology. An amino acid, right? Guess what? An amino acid. I could be lying to you slightly, but this is basically what the structure is, and then there's like an R group. Right, AJ? Okay, thank you. So, what is it? Amino acid. There's an OH group here someplace. Anyway, okay, I'm looking at this side over here. This side over here has the ability to accept an H+, and that's the component that's basic. So if you ever see NH2 on the end of something, it's basic, okay? So that's called an amine group. So this is basic. We immediately said Kb, icebox, boom, done. This is a salt, but then what did you guys further say? Okay, so then YKA. Okay, so it's a basic salt. So we know that this sodium is coming from sodium hydroxide. This chlorite is coming from hypochlorous acid, which is a weak acid. So we already know it's a basic salt. That's our hypothesis. And then so from that, the strong base made with sodium hydroxide, which we can't use, right? So you're using the ion that Vinky used for it to tell me chlorite, right? Plus water equilibrates to what? And that's the case of the OH being made, which confirms that we should be using a KB. So then icebox it up, solve for X, same thing like we did there. Okay? Who had 3? Levi's group? Okay, go for it. Somebody there?
So NH4 and CN, they both form a weak acid and a weak base. So when you find the K, you plus CN.
Okay.
And then you compare the two, and whichever one's greater, you would plug in the negative law.
So I'm just going to say whichever one's greater, we'll determine if it's acidic, basic, or neutral. For the weak salts, I didn't show you guys how to find pH, but we will with our buffers later. Okay, so you will compare the Ka of, the Ka of ammonium, because it's acting as an acid, and then the Kb of CN, because it's going to act as a base. And compare those. Good. Who had group? You guys group 4? Okay.
You have to set up a PDA chart. Sometimes you can use it.
Moles of whatever's left, right, of excess divided by total volume.
And then, I don't know, just the concentration.
Whatever this is, it might be H plus, it could be OH minus, right? And then find your concentration and then plug it into your pH formula to pH. Good. So that's an interesting one. So you actually have to react it before you can pull anything else out for pH. Group 5.
It's a weak acid.
Ka, and okay, so find X, and that would be equal to what? What ion of interest? H plus, and then we find pH. Good. AJ's group?
So this is a salt. So when you think about the two reactants to form that salt, you can use hydroxide and hydrochloric acid.
Okay.
And since both of those are strong bases, strong oxygen.
Is that one strong? Remember on the B, it goes lithium.
So in that case, you have to find the K of magnesium hydroxide.
So this is a weak base is what you're saying. This is a strong acid, so you already know it's going to be an acidic salt in itself, so the pH would be acidic. So which of those would make an H plus? It would be weird, but it would be magnesium hydroxide or magnesium ion pulling away a hydroxide to leave it alone in H plus, and then find that. Magnesium hydroxide is on the bridge actually between strong and weak, so I usually won't give you that one too often because it's an interesting one. So, okay, I'm gonna stop for now. We have a lab. The lab's gonna have shared information, and then from there, I think you guys are good with your mixtures. So on the lab sheet I just passed out to you, it is called acid bases and pH lab. I think you guys are going to be awesome with this. But what I'll do to kind of help our process along so that you're not finding the pH of every single solution here, you guys have seven samples, and those 7 samples, I'll have you guys get into 7 groups, or if I need to be a group, I'll be a group and I can set that up. But you guys will have 1 reagent assigned to you. You're going to prep the solution and then find the pH with the pH probe. This is really making sure you know how to use pH probes and find the pH using math and table logic or table icebox setup, and then comparing that to your pH probe. So verifying that your math calculations match up with the probe reading. Also, you're going to learn how to do serial dilutions. Who's ever done serial dilutions? Okay, a couple of us have, not many. But from there, you're going to have under part 2, part 3. You see part 3 where it says serial dilutions? Okay, so you're only going to need, 5 250 ml beakers, which you may not need exactly that much. But what I'll do is I'll cut the volumes. We'll go ahead and cut these now, just so that it'll help us with no waste and help us move a little faster there. You're going to take 10 to 20 milliliters. If you want to stick with 10, that's going to be what you'll utilize first. 10 milliliters of hydrochloric acid, 0.1 molar. That's your that's your first pH that you're going to be finding. A serial dilution takes a portion of the initial and you put it into the next beaker. You mix it, and you take a portion of this and you put it in the next beaker, and then you mix it. And you take a portion of this and you further dilute. It's called a serial dilution because it's a specific amount each time. But what you'll see is I cut these down. So those 10s all will be cut down to 5. Cut those now. You see that under part 3? It's also under part 3A and then part 3B. You see sodium hydroxide on the other side of the paper. So all the 10s will go to 5 milliliters, and that means all the total solutions with water that were 90, they'll be cut down to a total of 45 milliliters of water. So I'm just basically halving those so that it doesn't waste our reactants. And then I think from there you guys will be good. But I'm going to go ahead and ask you guys to get in groups so I can tell you which reagent you're going to test. And then we'll just leave the pH probe in it so that other people can see it. You will have to grab, I'll show you the back, pH probes and then the logger probe system. I think once you start reading, you'll be fine. But I'll leave that right there. So let's get into 7 groups if possible. I'm missing Jacob, so that's 16. 7 or 8 groups. So get in groups of 2. Get in groups of 2. Let's do that. Groups of 2.
Unemployment.
Alright guys, send something to come with like the materials. I will assign you a solution as you go. So guys, step 1, set up your pH probe. And let's not first set up, because I think I can help you with this expediting time. You will likely want a clamp to help keep the pH probe upright. Upright means that it's not turned to the side. There's a glass bulb in the bottom of it, and you can just attach the clamp to the your stand or something else. But the buffer that the pH probe lives in is really, really prolific with life. So I'm going to give you some parafilm as well. There's a lot of times we'll get mold spores that like to grow in the solution. And so we don't leave that too long. Alright guys, so pH probe storage for now, okay? Listen up. You need a beaker, just a small beaker, like 100, 200, something small. And you'll pull the blue probe, you'll pull it out of its little container really carefully. And as you split it out of the container, you'll see the buffer solution is floating around the bottom. I'm coming around with carousel so that you can cover that up so I don't want you to spill your buffer solution. So basically what I'm saying to do is this will get, just you wiggle it out. You see this? Okay, so this is the glass bulb on the bottom, which is fragile. And so they're going to have a little beaker of DI water to set this in with their clamp holding it upright. And so this buffer solution, which are still on my hand, it's fine, but bacteria and fungi like it a lot, so that's why I'm being careful. If you grab this off. Oh,
water pH for 1B, I think is what the question is. 1B pH. I'll put on with a 7 pH just to make sure it's fairly close. And then you guys are good to move on to the next part.
Oh no, it's gonna do it over the same.
Oh my God. Okay, hit 45.
Yeah. I just
Whenever you need a clean, occasionally, so this is the last I usually just start
flu. But I don't ever get the flu shot, so nobody get too close. Okay, so look up here with me. Look up here. Ready? So we know that different acids, being for this one, diprotic acids, have two different Ka values established for them. Because it's diprotic, the first ionization has a larger Ka value than the second ionization. What should that immediately tell you? Okay, so the second ionization doesn't happen as favorably in the forward direction. Also, the first ionization, which I have written out here, makes a more significant amount of hydronium ions than the second ionization even will attempt to. So many times our diprotic acids, if you're trying to find the pHs of them, you'll do the first ionization by delivering 1H plus, set up your Ka1, x squared over 0.1. I'm neglecting x. Most of the time you're able to in weak acids. Once you solve for x, you get 2.07 times 10 to the negative fourth. Plug that into pH, you get a weak acid pH. So 3 point something, that's about 4. That's right between the 1 and 7-ish pH scale, so fairly weak. So if I were to move on and find the rest of the ions, I would take this value of x, these two values here of x, and I'd plug them in here. And that's 4, sorry. And here. 2.07 times 10 to the negative fourth. Because this X, which represents each of these ions, as you go through the second ionization, you use the first ion, you make more hydronium, and those are your initial values in your icebox. You proceed through equilibrium. What you'll find is that this does not make a significant amount of H3O plus again. So, like we said, the pH is really controlled by the first ionization. Yeah?
Do you ever not neglect X?
Yeah, you do not neglect X when K value is greater than 1, or when K is fairly large. But for weak acids, all Ks are less than 1. Fairly small, actually, like 10 to the negative 7th and 11th. So yeah, you're generally able to. And on my paper, the percent ionization is like someplace on here, 0.2%. So it's definitely less than 5% you're able to neglect. So, but what I want to show you is the little part on the bottom where you have all those equations. And what you have to do is you have to look at a reaction. You have to figure out if something acting as an acid or base, and then you can find the K values based on that. What you'll notice, everything throughout here is based on that first example with carbonic acid, bicarbonate, and then carbonate ion. So whenever you're looking at the Ks, this new K is going to be a variation of Ka1 or Ka2, or Kb1 or Kb2 if it's acting as a base. So we're just going to manipulate equations for a couple minutes. So what you do is the very first thing you do is look for water, because all of our acid dissociations or base dissociations, or even salt hydrolysis, they all react with water. That's the perspective that you look from. So with this ion, how is it acting with water? How is it behaving with water? It's what? Is this ion acting as an acid or a base? Because it's gaining, okay? So it's acting basic because it's gaining an H plus back. So I already know that this is going to have to be expressed as a Kb, okay? So Kb, which is going to be Kb something, Kb1 or Kb2. What you do is you look for the combination of ions that exist. Well, this is bicarbonate, and this is the original acid. So that combination represents Ka1. It would be Ka1 because that's the first, before ionization occurs, and that's the first product made of that ionization. So this would be Kb1, but how would I get Kb1? What's the relationship between Ka and Kb? So I'd have to do Kw over Ka1 to get Kb1. And so this value that's given to me is Ka1 above, like whatever it was, 4.3 times 10 to the negative 7th. I could take the Kw constant divided by the 4.3 times 10 to the negative 7th, and I could get the Kb, which is the equilibrium value for that first reaction right here. So let's look for another one. So this one right here, you're looking for water. You see water is a product, right? So what you're thinking of is how is this ion acting with water? So first off, you can see it's reversed. So I'm no one have to reverse this. So whenever I reverse reactions, what do I do to K values? Invert them, right? So I'm going to have to invert a K value shortly, okay? So how is this one acting with water? It's acting as a base because it's accepting again, right? So if I'm accepting, I'm going to have to see the difference between the two ions that are over here. So these two ions, is this coming from Ka1, the first ionization, or the second ionization? Second, because this one has no H's left, so it's from the second ionization. So it's acting basic, so I'm going to find the Kb2, because it's from the second ionization, but I have to do 1 over Kb2 because it's the reverse reaction. So it's showing how we can manipulate reactions and their K values to find the appropriate K that should express this reaction's extent. But what's Kb2, what's 1 over Kb2 really? Ka2 good over Kw, because Kw over Ka2 would give me Kb2, but I need to invert that, so I flip my fraction. Now you guys tell me this one. Next one. Maybe watch the process like I did. Anybody? So I know you're looking for water. How is this ion or molecule acting with water? So it's acting as an acid because you can see its hydronium is being produced, so H plus is being donated here. Okay, so it's acting as an acid, so I know I have a Ka, but which Ka? Ka1 or Ka2? Because it's the second ionization good, you can see that there's a lack of ions. And this just happens to be exactly Ka2. You look at it now, you're like, oh duh, right? I see the ion, I see it acting, react with water, I see the second dissociation happening. So it's just the Ka2 that we had above. Okay, let's do a couple more like that. Okay, so you see water. How's an ion acting with water? Okay, so this guy is donating an H plus to make hydronium. So first off, another thing I'm noticing is I have the reverse direction. So I already know it's going to be 1 over something. 1 over what? Ka2, yeah, because it's acting as an acid. So you do 1 over the value. What about this one? It should seem familiar. Is it just KW? It's what? 1 over KW. So what you should see is that KW, and this is autoionization of water. 2 waters ionized to hydronium and hydroxide. This is KW, but we've reversed it here, so it's 1 over KW. Okay, and let's just do one more. I think you guys got this. I'm going to show you another picture here. This one right here. Ka what? 1. Because it's the waters on the reactant side, it's reacting with the original acid. First ionization is occurring. It's nothing tricky, it's just the Ka1. So it's just making sure you can recognize which one's acting as an acid and base. So these are diprotic acids, right? We're going to start doing titrations a bit more next week, but more in-depth titrations, including a diprotic titration, which you got to work to today for me. We're going to do like a virtual one for now, but we're going to do that tomorrow, don't worry about it. But what you'll start to see is that the deprotonization process occurs twice, and so the very first one has the first equivalence point at a pH of about 6, and then the second ionization has an equivalence point at a pH about 12, and the pKa values are going to be denoted on things like this. pKa is going to be really important for buffers, which will be starting tomorrow and the next day for us. But you'll see titration curves like this, so don't be afraid. It's just a secondary ionization. You can guess what a tertiary or a triprotic one would look like. It would have how many equivalence points? 3. So they do look a little different. And then I don't think we need to do any more of these. If you guys are fine with it, you're good. Some of the background reading, and I was thinking about like how much I've tried to reinforce. I'm trying my best to reinforce about 75–80% of everything. Some of these like basic reading things like this with your NSMI readings, just need to go back and read again about this, like why the strengths of acids differ, what things are stronger acids, like the oxy acids with the high amount of electron density. And so like for this one, why is HF the weakest acid? Anybody? But tell me why, like down a column, so HFCl, so F's the top of the column of the halogen group, or iodines on the bottom, and this is the order of the acidity, so this is the weakest of this is a weak acid in itself, and this is the strongest of the binary acids. Why is I so much stronger? Yeah. When you say the density, it's more, there's a little bit more than that, yeah. So the electronegativity trends upward and to the right, so fluorine is more electronegative. So that actually means that it would be willing to pop off and give H plus room to kind of leave, but it doesn't happen. So a really large electronegativity generally means it breaks really easily. The truth is here is we haven't talked about all the acid and base, or all the atomic radii. The atomic radius increases to the left and down group. So if you have H bonded to F, they're fairly small. There's a lot of attraction between the nuclei and the electron clouds here. But then H with iodine is like huge. Okay, it's like ginormous compared to fluorine. So that makes it really quite easy for this to cleave because there's a huge distance. And so I'm trying to think of like magnets. Magnets, when they're close together, they'll attract, but magnets really far away from each other won't attract. And so the differences in this attraction between the two ions is very weak, so therefore it does ionize very easily. This is very strong, so it doesn't ionize very easily. But it's about atomic radius, so it's about some like random factor that we just have to discuss now, but really it's more in the spring. So I'm going to stop there for now. I have 3 minutes left. So the stuff that I'm going to ask for you, I'm going to take it up tomorrow when you guys are doing your diprotic stuff. Sorry. This stuff right here that I asked for today. I'll take it up when you do your diprotic, so if you have some questions for me, you guys can do that. But kinetics, I wanted to review with you today. Most of them really, your FRQs really weren't terrible. There are some of those very specific phrases you have to say to get your points, so we're going to keep working on that. But your test corrections for equilibrium, you guys got those before break, and we kind of reviewed some of those already, so I think you should be okay. But if you have questions for kinetics, just come in. I'll leave my door open during third. and come and ask me some questions, because that's been a little while. And you guys have your multiple choice for kinetics already. I have tentatively right now do Friday, and I pushed the holiday packet to be Monday, so you have the weekend if you need it. Is that better? Yeah. So in terms of other things, just make sure you're looking over maybe a Barron's book, or if you guys want to borrow. I have a Princeton book. I have a crash course book. I have other random books. I have an e-book. I don't know how to share an e-book. I don't think do that. But look over some things that you know that you haven't seen before, okay? If you need to clean up your lab, go ahead and clean up your lab.
We don't have to have really good questions like that.
For what?
Just like what day?
What topic you talk about? I trust you. Yeah, I trust you. Just because that's like a free test for you.